Hello everyone, my name is Bayron. I'm a PhD student in Colombia and I'm very grateful to have the opportunity to share with you my work on theoretical aspects of modified gravity theories in cosmology from Home 2023. This work is the fruit of collaboration with Professor Sabas Neceris at Instituto de Física Teórica in Madrid. Okay? It is well known that the standard cosmological model is suffering by many theoretical and observational problems, and that modified gravity is one of the main platforms displayed to investigate these alternatives. However, there is a huge number of possibilities, as you can see in this picture. Then, some theoretical strategies are required to understand the physics behind these theories. Here, for the sake of simplicity, I will focus in the tiny part of this map known as f of r theories, which are very representative among the plethora of modified gravity theories. In the future, we hope to extend these results I will show you to larger portions of this map. Okay, so usually we say that modified gravity corresponds to modifications on the left-hand side of the Einstein equations, while dark energy corresponds to adding an extra energy tensor with the specific properties on the right-hand side of the Einstein equations. However, it is possible to find a bridge between these formulations in the effective fluid approach. In this approach, we pack all the modified gravity terms in this new energy tensor for dark energy, which allows us to associate to modified gravity a density and a pressure, and more importantly, dark energy perturbations, which are far easier to interpret. In the specific case of f of r theories, this energy tensor for dark energy has this form. See that there are only geometrical quantities in this tensor, and from it we can obtain the f of r density, pressure, and of course the dark energy perturbation. So we get the perturbation for density, the pressure perturbation, the scalar velocity, and the isotropic stress. And very important is to notice that these quantities depend entirely on the dynamics of the potential phi and psi, and many time-dependent coefficients w, y, z, etc. So, having a particular f of r model, dark energy perturbations are completely characterized by these gravitational potentials. So the problem now is how to know the dynamics of this potential. Well, here is when the quasi-static and subhorizon approximations are very extremely useful. Looking at this picture for the evolution of the potential in lambda CDN, which is the standard cosmological model, we see that for the larger k corresponding to the green line, after the epoch of radiation matter equilibrium, which is represented by this vertical line, the potential decays and tend to be constant. Then we say that we are in a subhorizon regime and a quasi-static regime when we analyze scales well inside the Hubble horizon, and the potentials are approximately constant. Now, how to apply these approximations in the practice? So let's take the perturbation of the Ricci scalar as an example. This is the complete result for this perturbation term. And when the quasi-static approximation is applied, we neglect the time derivatives of the potentials. So we neglect these terms in this case. And for the subhorizon approximation, we favor k-squared terms instead of Hubble terms. So these terms h via potential are neglected also, and at the end we get this very simple result. In applying these approximations to the full set of Einstein equations, we get as an algebraic system from which we get the potentials and the dark energy perturbations directly. I will call this procedure in this way as the standard approach to the quasi-static and subhorizon approximations. However, from the last results, we note the following, and is that the pressure perturbation and the scalar velocity depend on time derivatives of the f function, which is just the derivative of the f of r function in terms of the Ricci scalar. So if f dot is given by this expression and the Ricci scalar is given by this, so we should conclude that f dot is approximately 0 given that it is multiplied by a perturbation, which is the matter contrast L time. So in that case, the pressure perturbation and the scalar velocity occurs these forms. The question is, what is the mistake here? Why we are not getting this, and why some terms are neglected and some others are not? So our main task is to provide a more transparent approach in order to apply these approximations, the quasi-static and the subhorizon approximations. We can track the relevance of each term by analyzing the evolution of new parameters inspired by the slow roll approximation used in inflationary models, so that the subhorizon approximation is translated to this condition on the epsilon parameter, and the quasi-static approximation corresponding to time derivatives of the potentials nearly to 0 are replaced by these conditions on the epsilon phi and epsilon psi parameters. The delta, psi and chi parameters are not necessarily small, as we will see later. So in practice, again, the perturbation of the Ricci scalar, which is this in general, when we apply the quasi-static approximation, we replace the time derivatives of the gravitational potentials by epsilon phi and epsilon psi parameters, and of course we track the time derivative of these terms, of these parameters, by other parameter. And then we apply the subhorizon approximation, replacing the Hubble terms, the time derivative of the Hubble terms. So we get this at the end. And applying up to second order in the subhorizon approximation and zero order in the quasi-static parameters, since these quasi-static parameters are always multiplied by a corresponding epsilon square term in subhorizon approximation, we just take this order of the approximation and we get this. So you can see here that the result from the standard approach correspond to the deepest modes, that is, when epsilon parameter is exactly 0. We also recognize second order corrections, and similarly for dark energy perturbations, we get the deepest mode solutions and second order corrections. One exception is the scalar velocity, which is purely a first order quantity in terms of the subhorizon parameters. So that the problem now is, what is the relevance of these corrections? In order to do this, we need a specific model to assess this. And two perfect candidates are the designer model, fDES, whose background is identical to lambda ZDN, and the very popular Hu-Sawicki model. Here, although we analyze both models in the paper, here I only will talk about the designer model to make more comfortable the presentation of results. Where for this model, for the designer model, we have the evolution of all the subhorizon parameters here. As mentioned before, the parameters tracking the derivative of the epsilon parameter are not small in general, as you can see here. And what we see that the epsilon parameter remains small below 10 to the minus 3, the dashed line, the black dashed line, for k greater than 0.067 inverse of megaparsecs. We say, therefore, that a safety region for the applicability of the Subhorizon approximation is exactly k greater than 0.067. Now, we compare the evolution of several perturbation quantities as given by the standard procedure or new scheme and a full numerical solution of the late time cosmology in the designer FOR model. So for k 0.1 megaparsecs to the minus 1, we see on the left hand side that the standard procedure and our procedure are very accurate with respect to the full numerical solution. And on the right hand side, we see that indeed the slow roll parameters for the potentials are completely negligible during matter domination and only grows at later times. However, they never reach the value 1. For the dark energy contrast, we see that both approaches are very accurate, highlighting that our new approach here is providing a more accurate description by several orders of magnitude. More visible is the standard prediction for the scalar velocity, the green line, which completely disagrees with the full numerical result, while our method qualitatively agrees with their numerical result. As expected from the early discussion, the scalar velocity is not as small as predicted from the standard result, which is approximately 0, and in our case is a linear term in subhorizon parameter. Something similar is expected for the pressure perturbation, and changes in this pressure are related to the sound speed. And we see that both approaches give good approximations, of course, but again, our methodology also provides a better fit to this quantity. In the case when we are out of the safety region, that is k is less than 0.067, let's say 0.033, we see that our approach still provides reasonable accurate results, while the standard procedure is now inaccurate. For the density contrast, the standard case is up to 8% accurate, as you can see here, while our method is accurate at 30% level, which is fairly good. For the velocity and sound speed, we also find better results from our methodology in general. However, all these quantities are gauge dependent, so the natural next question is, what is the impact of these apparently relevant corrections on the cosmological observables? Well, unfortunately, the answer is basically no. As you can see here, the corrections only affect the CMB angular pair spectrum on the lowest multiples, and the effect is not particularly different to that provided by the standard approach. And the same story follows for the matter pair spectrum. This divergence here is typical when the quasi-static approximation is used, or the Subhorizon approximation, which in those cases k tending to be 0 imply larger scales, and the Subhorizon approximation is only valid for the smaller scales. However, I would like to emphasize that the main task of our approximation scheme is to make transparent the application of the quasi-static and the Subhorizon approximations. And therefore, let's say these negative outcomes in terms of relevance of these corrections to the main linear observables do not opaque the usefulness of our approach. Even more, our approach could bring to light incorrect results in other analyses. In this paper, the authors studied a designer-like model in Horndeski theories. They found that the standard approach implies a stronger gravity at late times, and, however, a preliminary result using our approach implies that gravity is indeed weaker at late times. A weaker gravity at late times is usually associated with a better fit for the f-sigma data, so it's a way to alleviate the sigma tension. And these results, although preliminary, an exhaustive analysis they require, they may be pointing out that a further analysis is required in modified gravity models. Well, in brief, the main goal of this work was to make transparent the application of an approximation scheme which is broadly used in cosmology to study the dynamics of modified gravity theories. Some terms neglected in the standard approach are found, but for the models analyzed, they do not seem to be very relevant at the observational level. However, FOFR is just an example, and things promise to be very different in other theories, such as Horndeski. Let me say that I really appreciate that you watched this video until the end, and I will be very happy to discuss about any concern you have about this work. Thank you.